Hi, everybody. Welcome to class today. I hope you guys are doing okay. So yesterday, we finished the linear algebra unit, and in past years, that was the end of the course, actually. But then they added in these 4 extra lessons, and then they moved some lessons. They took some stuff out of the first semester and moved 4 lessons from the second semester into the first semester. Anyway, we have this 4-day thing, and the topic is called limits, and it is, the course is called Precalculus, so you'd think that all the stuff we learned this year is stuff that you need in order to understand calculus next year. But you know that there are people who take pre-calculus and calculus in the same semester. So in theory, they take the pre-calculus is done in such a way that the topics happen that you need for calculus, right before they happen in calculus. But the reality is that that's not how it is really. And most of the topics you learn in pre-calculus don't help you with calculus at all. They're just their own sort of topics that you learn. This is one that definitely is part of calculus, and it's one of the most important parts of it. They usually start the semester next year with this topic. So this one is definitely going to be one that next year you'll be saying, oh yeah, that is, I'm glad, I was introduced to that last year because it's really helping me with calculus, as opposed to many of these other topics, polar equations, parametric, things like that. In BC calculus, they use some of those topics more than in AB. So what does this mean? We know what the word limit means in real life. What does it mean in a mathematical context? Well, here's a very basic function, constant function, f of x equals 5. And if you have to answer questions about it, you can say f of 1, well, that's going to be 5. F of 2 is also going to be 5. F of anything is going to be 5. But what you can't say, like officially, you can't say, therefore, I'll say that f of infinity equals 5. I mean, you could write that, and people will know what you're talking about. But we don't really write that because infinity is more of a potential thing that never actually gets reached. So you can't just say f of infinity equals 5, even though people would know what you were talking about. If you wanted to think of this function represented as a graph, then you could say, well, f of infinity, that's like the end behavior of this graph. So I could picture that way out to the right, since this is a horizontal line, every point's going to have 5 on it, including the points that are all the way off to the right. Well, the official way of writing this concept is over here. This is the notation for it. I'll make a new page for that. So they write LIM, which stands for limit, the limit of f of x as, and then down here they put a little underneath an x, an arrow, and something. It could be, in this case, it's an infinity. That is a well-defined math thing. The limit of f of x as x approaches infinity is 5. And this limit concept could have been introduced in some other topics. Like, for instance, when you did last semester and also last year, infinite geometric series. When you would casually put an equal sign here, and by the way, what does this, if if we're even allowed to put an equal sign for a thing like this, what would go on the right of the equal sign in this case? Yes, I saw a 2. I saw a 1 also. The 1 is the 1/2 plus whatever, but this extra 1 in front makes it 2. So we would just put that 2 there with the, sorry, just put that equal sign kind of casually. A better thing to put than an equal sign would be to put the words converges to 2. But the best of all, if you want to use the most like rigorous mathematical language, would be limit as n goes to infinity of the sum of 2 to the n as n, sorry, 2 to the k as k goes from 0 to n. That would be like the rigorous way of saying this concept. The idea is that the bigger n gets, the more terms there are. And this would turn into, this is 2 to the 0 power is 1, and 2 to the, sorry, not 2 to the k. I meant 1/2 to the k. Or 2 to the negative k would have been good also. Anyway, so this lim, you will see this a lot in calculus, this idea of this, of this idea. Now we've encountered this idea in graphing with asymptotes already, but this is like more formal. Okay, here I have a more complicated function, 5 plus 1 over x. And g of 1 is going to be 6, and g of 2 is going to be 5.5. And I can't say g of infinity, but I can say lim as x goes to infinity of g of x. What's the answer going to be then? You can type it into the chat. What should we say for the answer to this bottom? And the answer is going to be 5. Because as x gets bigger and bigger, 1 over x gets smaller and smaller, which makes this thing get closer and closer to the number 5. Now in the diagram, in the graph, I have a graph here of 5 plus 1 over x. You can see the hyperbola, and you can see that this is really a question. If I'm thinking of a graph and not just this abstract function, but I'm thinking of a graph, I'm asking, what's the horizontal asymptote? Horizontal asymptote is y equals 5. Sometimes, like last year in Algebra 2, they might have called it end behavior. They even suggested this, like in regions, they would be like, as x goes to infinity, y goes to 5, something like that. That was all just ways of hinting at this concept and this notation. So for today, it's like, what does this even mean, limit? And I want to give you some experience with that. Okay, here I have a more complicated equation, 3x minus 11 over x minus 4. And they want to know what's the limit as x approaches infinity. Does anyone want to type in what they think the answer to that question is, just to get like a feel for what's going on? It is going to be 3. We can think of it as from last semester when you did rational functions and you did horizontal asymptotes. You might remember that the horizontal asymptote, you would take sort of the largest power, and if they had the same if they have the same degree, you would just take the ratio of the two coefficients. So horizontal asymptote at y equals 3/1. So the horizontal asymptote and the concept of limit of f of x as x approaches infinity, those are actually the same concept expressed in different ways. One requires like thinking about some sort of graph. But this concept of limit is true even if the idea of graphing was like never invented. It's true that that function gets closer and closer to 3 without, it never actually gets to it. And yes, the 11 and the 4 are like not important towards this because for such big numbers, like you put 1 million in. But it's really a subtle concept because you might say, okay, well, if I put 1 million in, it's not going to be exactly 3. That 11 and the 4, who's to say this isn't like approaching, 3.15 zeros and then like a 3. The unit, so in the fall, the right in the middle of the fall, this unit, it was called rational expressions. You had like asymptotes, horizontal asymptote, vertical asymptotes, like strange looking graphs. It would be right in the middle. They would have reviewed polynomial graphs and then done these asymptotes, verticals, sometime in the second 6 weeks, I would think. Okay, now, there are other types of limits besides the limit as x approaches infinity. We could also do the limit as x approaches negative infinity. And what do you think the answer to this question here I'm looking at should be? Okay, I saw a couple of different answers, but 3 is the correct answer. Now, the graph reveals this because, yes, it's underneath, it's below the asymptote, but it's still like getting closer and closer to 3. It's like 2.99 something, and this one here is 3.00 something. But they both have the same answer. Now, that's not always, these two answers are often not the same, but in this case, there are. Now, you could also ask a question like this: limit as x approaches 4. So you could be approaching a finite number. Now, you see this funny plus sign after the 4? It's kind of a weird, oops. It's strange. You've probably never seen a plus sign in that location before. And this one has a minus sign in the same location. Those two questions actually have different answers. 4 with little plus sign means that if the number is slightly bigger than 4, like as I get closer and closer to 4, but from if I'm thinking about the graph is from the right-hand side, but if I'm thinking of just numbers, it's like 4.1, 4.01, 4.001. What's the answer for this question over here? By the way, can someone tell me, can you see the arrow? Is that something that actually comes up on the screen share? Oh, you can. Okay, so this could be really useful then. I could use this as a pointer. So yes, the answer for this question is infinity. Because as I'm on the right-hand side, it goes sort of up as high as possible as it gets close. But putting for this other question, what's the answer for this question over here? So that can have the same answer. And this one's actually, it actually is negative infinity for the second question, because here's 4. And as I'm on this graph going towards x equals 4, like x equals 3.999 or whatever, see how it goes, it's really, it becomes negative infinity. Now you might be thinking now that there's got to be an infinity involved in a limit. Like if there's an infinity here, you get a numerical answer. If there's a numerical number here, you get an infinite answer. But I could also do something like limit as x approaches 5. Because here at 5, it wouldn't matter whether I put a plus or a minus there. And when that happens, you don't have to write either of them, but just to write something that I'm going to put a little plus there. Anyway, in this case, I'll just write down x is, doesn't matter. Yes, in those situations, you actually don't have to put a plus or a minus there. Incidentally, the infinities never get a little plus or a minus. It's implied that if I'm going to infinity, I'm definitely going from the left-hand side. And if I'm going to negative infinity, I'm definitely going from the right-hand side. So we don't write those in. So when this happens, what's the answer, by the way, for this question I'm posing now? Limit of the function as x approaches 5. Ariel has to put an infinity, like emoji, or I don't know. How do you make that? How do you make an infinity into the chat box? Alt 5? I don't have an alt. Oh, option. Infinity. Very good. Okay, what's the answer for this question with the sorry, I got sidetracked there. I don't think it's 34. Just 4. Just 4, that's right. You could just plug the number 5 in. If you in this situation, since it's not like an infinity involved and there's not like a horizontal vertical asymptote, you could just put 5 in here and you get 15 minus 11 is 4, 5 minus 4 is 1. In that case, you could actually plug in the value itself. So the answer was 4. So that's the idea behind limit. I should quickly mention, you might wonder, is that exactly the same thing as saying f of 5 equals 4? It seems like it's like basically the same thing as saying that in this situation where you're not going to an asymptote or anything. But there is actually a subtle difference, because there may not be, there may be like a hole here at 5. And if there's a hole at 5, it would still be true that the limit as f of the function as x approaches 5 from the left and the right would be 4. But f of 5, and sometimes you can have a dot hanging out up here. So you could say f of 5 equals 6, and that's okay. So there is a subtle difference. Like imagine there was actually a dot there, like this is kind of a weird function that had a hole in it and then a dot elsewhere. Okay, here's an example. This is a function that's known as it's called when there's a jump like this, it's called a discontinuous function, kind of like a piecewise function. Would you take a minute to look at these 1, 2, 3, 4, 5 questions? And you could chat about what you think the answers for those 5 questions are. I'll put arrows at the ends of these. Okay, anyone want to, you can unmute if you unmute and say the answer for the first one. Whoever the first one to do that is. What's the answer for the first question? This one over here. Is anyone talking? I don't hear anything.
I think it would be infinity for number one.
That's right. The first one is infinity. Someone else want to say what the second one is?
I think it would be negative infinity.
You are right about that. And look at these two questions, which actually have different answers now. And maybe all three have different answers. We'll see. What do you think about this one? Limit as x approaches 1 with that little plus there. How is that different? Someone could tell me the answer to all three of those and explain if they think that they have all different answers or if they all have the same answer or something else.
I think as like with the 1 and the plus sign, I think that would be 5. And then I think the other two would be 3 because there's like the open circle on the black line. Okay. I mean the closed circle on the black line.
That's right. In calculus, they call it discontinuous function. And they actually define a discontinuous function as one where there's a point where the limit on the left limit and the right limit are not the same. Now, the rest of this lesson is about what if we don't know the graph? Because this whole limit concept exists whether or not anyone ever thought that you could graph stuff. So when you have a polynomial, like something of the form ax to the n power, start with that, simplest type, and this is going to infinity, that's going to be infinity. But if it's going to negative infinity and the exponent is even, it's going to be infinity here. But if this is negative and the exponent's odd, it's going to be negative infinity. I know we're used to like picturing, you know, even exponent versus odd exponents. And yes, graphs do help to visualize what's going on. But this limit word is a word about describing a function. It's actually not a word describing a graph, although the graph can be a handy way to help you understand it and think about it. Okay, but what about more complicated? Oh, okay, now this situation, we have a constant in the numerator and some kind of a ax to the n in the denominator. And that's another sort of basic one that we're going to be able to build more complicated ones eventually. You could type into the chat, what's the answer for this question? And 0 is the right answer. And you might remember from the rational functions graph that when the degree of the denominator was bigger than the degree of the numerator, there was a horizontal asymptote at y equals 0. So those two concepts are kind of related to each other. But what we have right now is that if you have a ax to the n, you're going to get infinity or maybe negative infinity. Whereas if you have something, you know, constant over ax to the n power, that's going to go to 0 as x goes to infinity. Now here's a situation where both, see in this one from before, of course, if the numerator is constant, and the denominator gets bigger and bigger, it's going to get closer and closer to 0. But what if both the numerator and the denominator have variables in it? So now it's like if you plugged in the infinity, you'd get infinity over infinity, and what's that? Is that equal to 1? Is that, what's going on there? But the trick here is, if you can, you reduce the fraction. Oh, I really should keep writing lim x goes to infinity 1 over x. You're allowed to do that. You are allowed to reduce the fraction. And that's the case we just did with the constant in the numerator and the variable in the denominator. I'll know what you're talking about if you don't write this again. It's kind of implied, but it's not equal to 1 over, is it? This limit is its own abbreviated way of saying like a complicated idea. So you are allowed to reduce the fractions. Okay, does someone want to say what they think the answer to this question is? Feel free to chime in. Oh, I see a lot of people wrote 2/3 in the chat, and that is the right answer. You can cancel those out, and then if the constant, if it's just 2/3, constant function is 2/3. You might remember this from the rational graphing horizontal asymptote at y equals 2/3, because you would, if the degree of the numerator and denominator were equal, the horizontal asymptote was no longer at y equals 0, but instead was the ratio of the leading coefficients. So that unit about graphing rational functions, I mean, that topic was not the most important topic in the world, with all the asymptotes and sign charts and strange. You might remember you'd have like graphs with all these asymptotes. You'd have like things that look like that. Maybe the whole point of that was to get us thinking about limits, which is a really important idea in calculus. Some of the topics in pre-calculus, we could really do perfectly fine without. We have talked in the math department about like, what if we just changed pre-calculus into a 1-semester course, just took half of it, just threw out half of it, and just taught the other half, whatever the better stuff is. You'd be perfectly fine in calculus. Now, it's my job to teach pre-calculus. That's my primary thing that I teach. I like, the topics I hope are interesting and thought-provoking, but we could, there's nothing, some of the topics don't really, go anywhere. Don't go anywhere, for calculus. I mean, in higher math, some of them do. Okay, I'm almost done with this lesson. Here is a more complicated expression with the numerator having a bunch of terms in it. And when that happens, you are permitted and this actually isn't always true in all types of math things, that you could split stuff up, like, like a plus b squared, is not the same thing as a squared plus b squared. So you can't always just split stuff up and do stuff to the pieces, but with limits, you can. I know this is a mouthful to write all these limits and all. I actually don't know of any real shorthand. Okay, what's going to be the answer to this question now? You could type it in. It's not going to be infinity though. most of these things, but it is going to be 2. Remember, most of these things, when you reduce, you end up with the case where the numerator is a constant and the denominator has a variable in it. And this piece over here, when you reduce, turns into a constant function, like a horizontal line. And that's why the answer is 2. Now, I'm going to give you like a heads up that tomorrow or Monday, I have another limits lesson with some more advanced like scenarios that come up. And then the last 2 days, we apply them to 2 of the most important concepts in calculus. So today's pretty easy. In fact, I think I just have one last question here. Now for this question, there probably is like a formal way of doing this. Oh, why does everything cancel? In the last example, all of these terms became 0 because they eventually reduced to constant over a variable. Like just looking at that term there, 2x squared over 2x to the third, the x squares cancels out and you ended up with 1 over x. So that was constant over variable. Remember, that's what happened over here. Okay, now good news for you here. We're not going to have to, and yes, if there was a 4th power in the numerator, the answer would have been infinity. Okay, I'm going to let you now for this one. What do you suspect the limit is based on stuff that you learned last semester? What do you suspect the answer is going to be? If we just were to jump straight to the answer for this question, what would you suspect it to be? Yes, it would be 2/3. Now, remember we talked about last semester, maybe or your teacher told you about how the horizontal asymptote, all that mattered was if these degrees are equal, it would be the horizontal asymptote would be the ratio of the coefficients. That's what's going to end up here. Even though I'm not doing this formally, like splitting it up and doing the pieces, it's true. It's what you would expect. So like on a test, I might have you I might say show, rigorous. This is like the rigorous way of demonstrating this limit. Whereas this one was more informal. I didn't it didn't get broken down into fundamental things the way that this one did. It's just more, this one's more like just the gist of what's going on. Okay, well, that's what I wanted to show you today. Limit starts slow, and on Monday, it kind of gets clever. There's all these clever tricks that come up. But then on Tuesday, and then no class on Wednesday because I have a meeting. Tuesday and Thursday, we're going to really do a lot with these limits. Let me pause the recording.